Okay. I believe you.
Arrangement, maybe this one. What about this?
Nope.
Oh, wow. Okay, this is really acting up today. Okay. I'm just gonna do it like this. Sorry about this thing. We've done it before. I don't know what happened today. I've learned something today though. Zoom has a new feature for noise cancellation, voice noise cancellation. Okay. This should work.
Yes.
Okay, great. So thanks, Elizabeth, for the introduction, and sorry for the delay. So I am going to give a talk, which is a mixture between a seminar and a colloquium. If you want to blame someone, probably you should blame Elizabeth for that, to pick the subject. So the most part of the talk will be like colloquium style. It's about quantum physics, how topological physics, how one can get some of these topological ideas, bring it to photonic systems. And then depending on how much we discuss, etc., I would have another part which is more like correlated systems, how we can use cavity QED techniques to manipulate strongly correlated systems. And this is the second part would be more theoretical. And please ask questions. Although this is online on YouTube, I prefer to get some questions on while I'm giving the talk. So I'm talking about photonic systems, and for that it's better to talk about the building blocks in photonic systems. So for that we can think of resonators, that you can form a resonator at any frequency in the electromagnetic spectrum, and it can be in telecom regime, it can be in the visible regime, it can be in gallium arsenide, different material, it can be in silicon, it can be all the way to microwave domain where we have qubits. So this is basically the building blocks of a bunch of resonators that will couple them to each other. Sometimes we can be linear like these ones, no interaction. Sometimes we can be highly nonlinear and then form a qubit. But in most of them, in most of these photonic structures, when we nanofabricate them, they are disorders. These are not exactly the same, their frequency don't match. The frequency of these guys don't match. We have to fine tune them most of the time. And it would be nice to have a situation that we have built-in protection, that regardless of how we make our system, there will be some built-in robustness. And that brings the idea of topology. And again, for the expert in the audience, I apologize. This is a very high-level introduction to topology, in particular band theory topology, appropriate for undergrads, but that's what I was advised to do. So topology is a part of math that deals with objects with same topological properties. Basically, we call them same things, topologically the same, when we can continuously deform them to each other with no cutting and gluing. Usually people give the coffee mug example. I would like to give another example, which is something that I would like to go at some point when the pandemic is over. And that's an island. We call an island regardless of its shape. It can be rectangular, it can be a circle, it can be heart shape. You always call it an island regardless of its shape. But if this island happens to be connected to some part of a land, then we can call it a peninsula. We never call it an island, regardless again of its shape. So all kinds of islands are topologically the same, and all peninsulas are topologically the same. So no matter how you deform them, you can island and peninsula. So what? So now if you want to swim around an island, you can start from one point, then you can go many times back and forth, clockwise or counterclockwise. You can assign always an integer number of times that you can go around an island. That doesn't change. Shape of the island doesn't change it. The way that you circle around the island doesn't change it. The path that you take doesn't change it. It's an integer number. But if you want to do it in a peninsula, you cannot do it. That's always 0. So that integer is always 0. So now, what is the physical consequence of this? If you can relate a physical observable to these winding numbers, that integer, then those physical observables will be guaranteed to be robust against deformation. So if we can manage to do that, then we are in gold. We can do something useful. Then the fabrication disorder, the parts of the error that we have in the system is not going to play a role in the physical observable that we are measuring. So that actually happened. Of course, it didn't happen by thinking about topology and then doing the experiment. It was the other way around. It was a serendipitous experiment that then theoreticians realized that it's relied on topology, was the quantum Hall effect. Various forms of it, various manifestation of it in different material, basically topological physics in electronic systems. So the original experiment was a two-dimensional electron gas and the presence of a magnetic field perpendicular to the system, and then the measurement of the resistance in the transverse direction. So you have voltage in one direction and then current in the other direction. And what was remarkable about this was that when you look at this Hall resistance as a function of magnetic field, you have these quantized values. These values do not change from sample to sample, and from if you change the temperature a little bit or if you change the disorder. Their location is given by a bunch of fundamental constants and an integer. And it's quite amazing that they just rely on that and not on the details of the system. And that's why people use it for standards for resistance. And the reason, very quick reason for this is that when you have a magnetic field, you have an electron and you have cyclotron motion. So you have a perpendicular magnetic field and the electrons will go around this magnetic field. But in a semi-classical picture, which is this electron orbiting around the magnetic field, if we get closer to the edge of the system, the electron cannot finish its path and it would skip around the orbit. So it would have skipping orbits. Basically, it cannot finish it, so it would skip on this direction or in that direction. So in the bulk, the electrons will not be conducting. They will go around and will not produce any current, but at the edge they would produce. And now what is cool about this is that if the edges has some dent or some problem, then it doesn't matter. This skipping orbit will just go around that dent and then continues its way, and that's why it becomes robust. And I will come back to this concept again. So the question that we asked a long time ago was that, about 10 years ago, was that is it possible to have similar effects for photons, right? So we would like to have some kind of similar robustness in photonic systems. So photons don't have charge, and they cannot see magnetic field as strongly as electrons. So what should we do? If we cannot make it, we should fake it, and we should synthesize it. But before going and showing that how we can synthesize that, why are we interested in it for photonic systems? In a photonic system and in genetic system, you have a waveguide. You want your photon to go one way, but then again, because of disorder, you have some impurity in the system and it will backscatter. But if you can have a topological system for photons, then it should go around the impurity unimpeded and then continues its way instead of getting backscattered in the system. So basically, we are looking for robust solutions of the Maxwell's equations. All I'm talking about for the next 10, 15 minutes could have been discovered at the time of Maxwell's. We didn't need to know quantum physics, etc., to discover these kinds of modes. They are basically some solutions to the Maxwell's equations that are robust against dielectric fluctuations. But we had to wait many years to learn about topology and quantum physics, and now go back to photons. So now, as I said, photons are weakly interacting with magnetic field. Magneto-optical properties effects are very weak in the optical domain, particularly. So we have to synthesize, and then that idea is very simple. So we assume that we can have a two-dimensional array of ring resonators. So these are a bunch of waveguides that form a resonator with different size, like white ones and gray ones. And if we want to really have a non-zero magnetic field for these photons, if we want them to feel the same physics as electrons in a quantum Hall effect, then we have to make sure that if a photon hops around a single plaquette, it would acquire a non-zero phase, similar to R-on-1 phase for an electron. So in order to do that, you just take two resonators with with the same length. M is an integer number, lambda is the wavelength of photon that we want to be resonant at, and then connect them with a ring that is anti-resonant with these two. So its perimeter has an extra length of lambda over 2. So I can constructively interfere with myself when I'm over here, but if I scatter through this region, I should destructively interfere with myself, and then again, I constructively interfere with myself. So if you follow a photon, it will circle around, but there is some coupling over here. It can go to this side, it will go over here. When it comes out of this resonator, it will not go back to itself. It would not complete the circle because it's anti-resonant. Instead, it will go to the other one. But then when it wants to hop back, again, it will not go to the upper path. It will just take the lower path, as I showed over here. So when I'm going from right to left, I take an optical path that is associated with this, with the top part. And when I'm going from right to left, I take it from the lower part. And if I asymmetrically position this resonator, this middle resonator, then the accumulated phase is different when I go from left to right and when I go from right to left. So in the second quantized formalism, when I'm hopping from left to right, this is the annihilation operator of a photon in resonator AX. This is creation of a photon operator, a photon in resonator X plus 1, this one. And then the accumulated phase is something that e to the minus 2 pi I alpha associated with the optical path difference. Sounds good? So now, if we arrange many of these links such that we can implement such a Hamiltonian, in particular, we arrange them in such a way that we acquire a non-zero phase around this plaquette, and all the plaquettes, then we can have like a Hamiltonian of a charged particle on a lattice that feels a perpendicular magnetic field. And the spectrum of that is known since the time of Hofstadter. That's Hofstadter butterfly spectrum. This is the eigenenergies of the system when you put them on a closed boundary condition. These are the eigenenergies, and this is the magnetic field strength, alpha, characterized by this. Then when the system is on a torus or a closed boundary condition, you have these magnetic bands. If you open it, you will have the emergence of some states that appear between the magnetic bands, and those are the edge states that we would like to study. So in order to implement this idea, you can use the silicon on insulator technology. The previous figure was schematic. This is a real figure. It's an SEM image of silicon rings on silicon dioxide. And you can see typical numbers of the ring size, thickness, etc. Now we have engineered these resonators such that they are off a little bit from each other. And when they go around the plaquette, they would acquire a non-zero phase. What is good about photonic systems is it's leaky. It's a bug, but also it's a feature. So depending on how many photons you have in each resonators, they can scatter light. And then if you put a microscope, you can see where that photon is, or where that mode is constructed. In other words, you can measure the amplitude of your wave function in your system, not the phase, just the amplitude of the wave function. So now, if we come with the frequency of a photon that is resonant with that edge band, you can go through the eigenmodes of the system that are associated to the edge states. If you come with a frequency that is associated to the bulk, then you go to the bulk state and come out. And if there is no resonance, then you would just get reflected off the system. So if you go to the edge of the system, and if you intentionally remove one of these resonators, as advertised, the photon will not backscatter into the bulk or go backward. It could go around the impurity and then continue its way. So this is a simulation. This is an experiment. This was the first experiment that we did. After that, we have, of course, better data, but this is from the 2013 paper. And it goes around its impurity and then continues its way. So now that was the imaging of the topological edge states. I would like to actually take questions, Elizabeth. I don't know whether it's allowed or I don't want to go too fast or too slow.
So there are no questions in the chat, but if anyone has any, please.
Okay, good. So that was imaging of the edge state. This system has been used to do other kinds of exploration of topological physics. And the first question that I would get around this year was that, okay, photons don't have charge, you don't have charge conservation, so what is quantized in this system? And you cannot have conductance. You have just transmittance or transmittivity, which goes from 0 to 1. So what is really quantized? And that's what we thought about generalizing Lofgren's argument for bosonic systems, in particular for photonic systems, and see whether we can observe the spectral flow. So for the experts, they know what it is. It's basically that when you apply, Lofgren's argument was that when you apply a flux into the system, you remove one charge from the inner edge or to the outer edge. And that's associated with the fact that you have these edge states, and when you pierce the magnetic field, their energy should shift upwards or downwards by just one, because after insertion of a 2π flux, you should come back to the same position. Now, if we do this for the photonic system, we should see the same thing. So then that was the observation of that. Similar to the Haldane model, one can implement a quantum anomalous Hall effect where you don't have the total magnetic field can be 0, but on sites it can have a staggered form. So on average, the magnetic field is 0, but on plaquettes, it's changing its sign, and one can implement the same thing. Another, it might be more historically relevant to where I'm giving this talk, is higher order topological phases that one could observe them. That's actually first observed in your institute, and actually theoretically was discovered there and then experimentally observed. We also use our system to theoretically, to experimentally look at it. Other groups have also used this platform to look at topological lasers. Is it possible to make lasers more robust? Can we have reconfigurable topological states? And that's pretty much it for kind of this platform. So far, there are many other platforms using many other parts of the electromagnetic wave, from my microwave domain to visible in free space, again, microwave, optical. And for this classical part of the business, there are 2 reviews, if you're interested. For people who are not familiar with topology and not familiar with quantum, I suggest this one, which is written basically for undergrads and non-experts, and the review of modern physics, which basically goes around all kinds of platforms and models that have been implemented until 2019. I have to say everything over here is all classical physics, and it's based on Maxwell's equation. So the aim of this talk is kind of to go beyond that, to see what can we do beyond Maxwell's equation in topological photonics. In particular, can we explore some physics that does not have electronic equivalent? So the outline of my talk is that I would like to look at two directions. One is the quantum directions in topological photonics, using in particular generation of photon pairs in this platform that we talked about. And then quantum optical interface, basically implementing these ideas now in photonic crystals, and then look how emitters can be strongly coupled to these topological edge states, and whether we can make topological waveguides coupled to emitters strongly, topological resonators coupled to these emitters strongly, etc. And then, depending on your question, I would like to now would like to then talk about quantum optics meeting correlated electrons, how we can use cavity QD ideas to manipulate correlated electronic systems. From Mott insulator to superconductors can be enhanced superconductivity using cavity QED ideas, etc. So if there are no basic questions, I would go to the first part of the talk. Just this one. So one way to generate pairs of photons is a very popular one. Way to do it is a spontaneous four-way mixing. You take an nonlinear optical material, you pump it with some frequency, omega p, you absorb 2 photons, and then you emit 2 photons with 2 different frequencies, omega s signal and omega I for idler. We have energy and momentum conservation, so the incoming frequency of the photons should be equal to the outgoing ones, and also the momentum of the incoming photons should be equal to the outgoing photons. You absorb 2 photons, you emit 2 photons. So this is the second quantized Hamiltonian for it. You annihilate 2 photons, and then you create 2 photons, and vice versa. So if these are like resonances in a resonator, you pump the system at this frequency, you generate idler and signal at higher and lower frequency. So in a nanofabricated system, if you want to increase your yield, you would like to have many of these resonators and then increase your yield. So you pump on, let's say, from the left, you go to many of these resonators, and then you generate your pairs of photons. Okay, this sounds cool, but there is a problem, because since these are nanofabricated, the frequencies are not exactly the same. So when you look at the joint spectral density, basically the frequency of the photons that are emitted for different devices, you see a strong variation, because in each fabrication the frequency mismatch is different, and that leads to strong modification of the transmitted light. In particular, if the system is very, very long, and if the disorder is very, very large, then we get Anderson localization. There is no propagating mode. Everything will be trapped, and the photon will be just reflected. Here is the precursor of the Anderson localization. The system is much smaller than the localization length. So can we use topology to solve this problem, or to address it to some extent? In particular, can we address this problem of conservation of momentum that in optics is called phase matching? In order to do that, we have to go back to the classical physics, the classical problem, no nonlinearity, no quantum, and see whether those edge states are statistically robust. What I showed was just an image. It was not really serious physics. It was more like the beauty. But here we would like to look at the system statistically, in particular looking at transmission as a function of frequency, and Wigner delay time, the time that it takes for photon to go from one side of the device to the other side of the device as a function of frequency, and then repeat it for different devices with different fabrication disorder, and then superpose this spectra on top of each other. This was a work that was led by Sunil for 15 by 15 systems. And what one can see is that if we tune the frequency of the incoming photon to be in the bulk, then the spectrum is not robust. From one disorder variation to another disorder variation, it changes a lot. But when we go to the edge, then it's robust. You see that it's completely flat, more or less experimentally, and then it doesn't change from system to system. So this tells us that these states are robust against imperfection. We can use them for phase matching. So now let's do it. So as I said, for the one-dimensional system, the one-dimensional array, indeed, when you do the experiment for different devices, it changes from device number 1, 2, 3 very much. But when you pump the edge, then the photons would come out primarily at the frequency band that you have engineered the system to be. So you see, these are related to different devices. They are very similar to each other in contrast to the one-dimensional. This is remarkable because this is despite the presence of a strong disorder in the system. The frequency mismatch we have estimated to be almost of the order of the tunneling rate. And also our magnetic field is fake. It's not uniform over the entire system. It varies from site to site. Nevertheless, we see the similarity. So these are experimental data, and one can actually do a numerical simulation and then see how similarity between different spectra changes as a number of resonators in the system, basically as a function of system size. So in a one-dimensional system, it just goes down. The spectrum becomes very different from each other. The spectra become different from each other. But in a two-dimensional system, it more or less stays the same when we go to larger and larger system. Can we make sure that these are indeed photon pairs? Yes, it is possible. The way that you make sure that these are photon pairs is that first you detect one of them, and then you make sure that the remaining is a single photon. So you basically herald it on the presence of one photon, and then you look at the probability of seeing two photons in the remainder. And that's basically the correlation function, G2 correlation function of a heralded system that should go below 0.5, and that's an indication of this photon pair generation. One can play other roles. One can not only generate photons at different frequencies, but we can also generate them at the same frequency by pumping at two different frequencies. So now we are pumping at two different frequencies, and we would like to generate them in the same band. The reason is that this has applications for many of the quantum information processes or boson sampling, etc., when you want to have two photons with the same frequency. So this was a work led by Sunil Mittal as a postdoc and now a research faculty in our institute. Vikram, my student who recently graduated, and of course Elizabeth, who used to be closer to us, and now of course she's here. Now after this part, I would like to go to the second part. Again, no questions. I think by being YouTube live, everyone is scared to ask any questions.
Yeah, don't see any questions in the chat.
Okay. Okay, so now let's go to the second part. Second part is quantum optics interface. Now we would like to have a compatible structure that could be integrated with solid state emitter. So the nonlinearity that I talked in the previous part was bulk nonlinearity. It was not strong nonlinearity mediated by emitters. Now we would like to integrate some emitters to mediate strong interaction between photons, or understand how light-matter interaction, strong light-matter interaction works in a topological system. In order to do that, we had to leave our ring resonator architecture and then look at another architecture, which is photonic crystal. So in photonic crystal, very similar to topological insulators, one can make a topological insulator. I don't use the word insulator for photonic systems because I don't think it's a good word. We don't have any Pauli blockade, or so the word insulator is not a good word for photonic systems, but this is an analog of that. Then you have a crystalline system, in particular, this honeycomb structure. If these holes are made in the same way, that it's uniform across the system, then we have this Dirac cone. But now if I take these unit cells and make these holes closer to each other or separate them from each other, these are holes in gallium arsenide. This is actually an SEM image. Then you can open up a band gap. So you can open up a band gap like this. You can open up a band gap like that. You engineer the system such that this band gap has a substantial overlap with this band gap. And the way that this band gap works is that it also inverts the band, meaning that the electric field that is over here has a different form than the electric field that is over here. And then this is, for example, p-type, that's the d-type, and for the lower band. And then for the upper band, the other one is d-type, the other one is p-type. And if we now put two of these regions next to each other, then we should see the emergence of topological edge states. We have not broken the time reversal symmetry, so if we have an edge state with one polarization going this way, the time reverse partner of it should be also present, which should have an opposite polarization propagating in the opposite way. This polarization is not the transverse polarization, is actually transverse and longitudinal. So if the photon is propagating like this, the electric field is kind of winding like that, going over there. So in person, there is an act to do that I learned from Arno Raschenbattel, and there is like a John Travolta dance that he pioneered. So sometimes I use that, but I think online one cannot do this. So what's going to happen if we put an emitter over here? So this emitter emits a photon, and its polarization, it can emit a sigma plus polarized light or sigma minus polarized light. Particularly, it has this structure that if you apply a magnetic field, you can have a Zeeman splitting. So your sigma plus light and sigma minus light would have different energy. So you basically relate polarization to frequency. Now, if I shine light on this and do photoluminescence measurement, meaning that I excite the system and I would like to see what kind of photons are coming out of the system over here, then you see two branches. This is wavelength, and then this is magnetic length, a magnetic field. If you increase the magnetic field, you see two branches associated with this guy and with this transition. Now, if I sit on this side, since the photons are only propagating using the red arrow, the sigma minus one, then I should only see one branch over here. And indeed, we see one branch over here. If we sit on the other grating, then we see the other branch. This means that there is this spin momentum locking. So the photons that are sigma plus will go this way and the sigma minus would go that way. Exactly what we advertised in the previous slide. Now, that is this that I showed was actually implemented in photonic systems with pooled nanofiber and also photonic crystals. And there is a nice review, chiral quantum optics. What is different in this system is topological. So what is topological? It should be robust against some bends and disorder, etc. And indeed it is. So you can think of these photonic systems, these crystal structures as Legos. So you should not break your Legos, but you can make any structure as you like. And if you put them exactly next to each other, you can create any kinds of bends, and the photons would not care about these bends. It would just go around the bends and then continues its way. So if my emitter is over here, now if it's emitting a sigma plus light, it would go over here, a sigma minus light would go over here, similar to the previous slide. And indeed, we see these two branches that emerge. And one can again do a G2 correlation function measurement to show that they are indeed single photons. So now, why these systems might be interesting, why this kind of chiral coupling an emitter to a chiral system would be interesting. There are two ways of thinking about it. One is that what happens to the photons that are in these kind of chiral systems. The other one is that what happens to the emitters that are coupled to a common waveguide in a chiral fashion. So let's first look at the first one. What happens to some photons that are propagating in a chiral system? I have my emitter that is coupled non-chirally. It means that this photon can be emitted both in the forward and backward direction, or it can be coupled chirally, so that when the photon is emitted, it will be only going forward. If you come a single photon like this, it would get absorbed, and then if this coupling is very strong, then it will be just completely reflected, 100% reflection. If you come with two, then you get excited. Some of them would go forward, and then some of them would go backward. You could just kind of get split. In a chiral system, you don't have any other option. You just get absorbed and then emitted, and then you go forward. If you if you send two photons, the story is the same. You cannot go backward. Two photons would go always forward. So then the accumulated nonlinear phase would always go this way. And the characterization of these photons are still ongoing. There was actually a very old work by Vladimir Yudsin on these waveguides, but there are even like recent works to understand how these photonics states can be characterized and can be generalized, like ideas like entangled entropy, etc., to characterize them. So that's the story of photons. One can also look at the emitters. One can integrate out the waveguide and then see what kind of effective interaction you get for spins. So if it's a non-chiral system, if you have a waveguide and then integrate out your waveguide, you get some master equation like this. Basically a Hamiltonian, that flip-flop Hamiltonian, that these two emitters can exchange a photon, and then you flip-flop like this and that. But then it depends on the distance of the system, the distance between two emitters. These two emitters, if they're close to each other or if they're further apart, they can form a resonant structure in between, such that you have this sign dependence for the Hamiltonian part. You also have the superradiant and subradiant part, that these emitters can actually spit photons outside, out in the waveguide, and that would also have sinusoidal dependence. Now, if you couple two emitters like this that are chirally coupled, then you don't have the option to go backwards. You always go forward. And the master equation is completely different from the previous master equation. In particular, these spatial dependence are gone. You just only have a phase that you can gauge out. So this is basically location-independent coupling. And Peter Zoller's group actually looked at how we can make dimers coupled to this system. This is work by Hanna Spickler and Peter Zoller. We have been looking at whether this can be used to address some of the problems in solid-state systems, that your emitters have spatial and spectral inhomogeneity, meaning that they're all at different frequencies, but also they are not located at the same position. One of them is over here, one of them is a little bit here. You want to implant an NV center or silicon vacancy over here, but it happens to be over there. If you can chirally couple them to a waveguide or to a resonator, then you are insensitive to that location, and that might be useful if you want to make a squeezed state out of these spins. So that's kind of the motivation, and the first work towards that is to have these photonic structures and then make resonators out of it. And as I said, this is like Lego. You can put these photonic structures next to each other like a Lego and make any resonator you like. You can, for example, make a triangular resonator. So the color corresponds to whether you have shrunken those unit cells or expanded the unit cells. So over here, you have two boundaries, one boundary over here and one boundary over here. These are the corresponding photonic edge states and with different polarizations. And now if you have a an emitter over here, it can couple to one of them and then come out of these resonators, these waveguides, first coupled to the resonator and then coupled to the waveguide. And then you see a strong enhancement, well, like a strong, what the modest Purcell effect of this emitter coupled to this topological resonators. So the Purcell effect over here is about the factor of 3. Okay. So this concludes this part, and which was basically the quantum optics interface. And this was a collaboration between my group and a group of EDOX, my colleague at JQI. Most of the work was led by Sabir Sachuparik, who graduated also recently. And these are some of the references. So if there is no talk, I will change gears and then talk about cavity QED of correlated systems.
Yep, sounds great.
Okay, people won't forget. Oh, Paul has a question.
Hi, yeah, I have a question about the chiral. Can you go back just a slide where you have the different emitters? Fine, that's one. So how robust is this to difference in the frequencies of those emitters? Because I guess if they're too far detuned, the photon just won't see it, right? It'll just
they're not
go by.
They're not robust against frequency at all.
I see. Maybe
they're only robust against spatial inhomogeneity, not spectral inhomogeneity.
Maybe on your next slide, I think maybe I misheard something then.
Maybe I misspoke. So we can be insensitive to the location of these emitters, not to the frequency of the emitters.
Okay, great. Yeah, okay, that makes perfect sense.
And it makes sense because imagine that I have like one emitter here, one emitter here, and one emitter here. The photon that reads this emitter has to go through this guy and then comes over here. But it doesn't matter actually where I put the second emitter. It can be over here and it can be over here. As long as it's chiral, it takes the same path. In contrast to a non-chiral system, that if I have 1, 2, and the third emitter over here, the dog did not agree with me, that if I put the emitter over here and over here, they form a mirror, and this is basically the mirror effect.
That makes sense, and yes, my dog agrees with you. Thank you.
Okay, good. We're all in agreement. Okay, no questions from humans and dogs? Okay. So, of course, this work on topological physics is continuing. Basically, if I want to summarize this part, is that we are thinking about topology as a new design principle for photonics. You can make resonators, you can make waveguides, you can make lasers, etc. And now it's basically a good time to ask questions whether it's useful. We are playing with these things, whether they are really more robust compared to conventional waveguides, conventional resonators, conventional lasers. And for that, we have to really do a fair comparison. We have to use the same material, same process, etc., on the same device, and then see whether which one is better or worse. One new idea that we are exploring, spearheaded by Sunil Mittal, is whether we can make frequency combs or robust frequency combs using these structures. And unfortunately, this doesn't work. Basically, you can make these nested solitons that go around the edge of the system. And if you remove one of these resonators or put some disorder, this soliton does not care, and it goes around the system unimpeded. Most of the things that I talked to you about was linear and weakly nonlinear. One can think of putting these ideas into a strongly interacting system, and think of making fractional quantum Hall states of light. So there are nice works this should be qubits, in Chicago, both on Rydberg and superconducting qubits, to look at fractional quantum Hall states. We have been also theoretically exploring these questions, in particular inspired by quantum simulators in Google. And that's that we have access to these quantum simulators. And if one day, let's say we make some of these many-body topological systems, how we are going to go about measuring them. The usual linear response theory that we have in condensed matter does not apply most of the time. So can we think of more alternative ways to measure these systems? Let's say the Chern number or fractional Chern number. In particular, in these quantum simulators, we have access to the wave function. We can measure the wave function properties and spatially resolve it. How can we measure fractional Chern number in that? And these are these two works over here that they just got published in collaboration with Benoit and Peter Zoller's group. So but that's a completely theory work on how we can use correlated correlation statistical measurement to measure many-body Chern number. And the theory collaboration was with Peter and Mason Barkeshley, again, my colleague at JQI. There it is. Okay. Now let's change gears. Correlated using cavity QED system, cavity QED ideas. I have 10 minutes. So cavity QED and in general quantum optics, in order to put it in perspective, we can think of this regime diagram. So on one axis, you have number of photons in the system. On the other axis, you have the interaction strength per photon. This is basically the fine structure factor. That is usually, we think of it, it's fixed, but we can modify it. So in free space, it's fixed. The strength of interaction per photon is just given by alpha. If you have low number of photons and weak interaction, then you're in the regime of linear optics. If you have many photons, weak nonlinearity, you can be in the regime of classical nonlinear optics, like solitons, etc. Now, if you put your emitter inside the cavity, then the chance of interaction between a single photon and a single emitter is enhanced, and then you can effectively enhance the interaction strength per photon. Then you reach the regime of cavity QED. You have strong photon-photon interaction, and that's where cavity QED is located. If you have many of these cavities and many of these photons, then you go to the many-body systems or correlated systems. One example is that like multi-insulators of photons, they're all interacting with each other, and then you have many of them. So this is basically the way that we understand quantum optics most of the time. But recently there is a kind of an emergent axis over here, and this is like a perspective in preparation that we're working on, is that this axis is this characterizes strengths of correlation in our matter, in our electronic system. So this was the strength for photons. This is number. This is the strength of electronic interaction or correlations. So diamond centers, quantum dots, etc., are located here. There are just individual emitters located somewhere. But now we can think of multi-insulators. We can think of fractional quantum Hall states of electrons that are now coupled to light. And then the question is whether we can use this light to probe them to dramatically change their effect or manipulate some of these states. So this is now the same phase diagram, or not phase diagram, kind of a regime diagram, tiled with different physics that one can explore. So in the weakly linear regime, if you use light in a non-perturbative way, you can think of Floquet topological engineering. You can have a non-topological system, you shine light, and then you make it topological. That people have observed it last year. Now, it's actually in the group of Andrea Cavalieri that it was experimentally observed last year through transport. Before it was at MIT through ARPES. Now, can we use this light to do some stronger change in a correlated system? Can we enhance superconductivity? Can we manipulate fractional quantum Hall states, electronic quantum Hall states in a system? Can we put them in a cavity and then come up with new phases of matter and light? So I have a few minutes, so I can go very briefly on a couple of projects that we have done, the theory projects that we have done on this front. And please stay around or ask me later if you're interested to get to know more detail. But I apologize, I will be very cursory and won't go through any details of them. So one part is on superconductors. Can we enhance superconductivity using light? So usually, if you shine light on a superconductor, you destroy it, but that's not really true. And this was known since a long time ago. That and it's called Eli-Ashberg effect. That if you shine some microwave radiation on a superconductor, you can actually enhance it. You won't destroy it. And this could be very understood in a very simple way. That you have a condensate of Cooper pairs, you have a gap, and then you have these quasi-particles. And then if you shine some light that is below the band gap, below the gap, you cannot destroy these Cooper pairs. Instead, you can enhance some of these quasi-particles to higher energy, basically evaporate them, and that effectively enhances your superconductivity. So the question that we had with Victor Galitsky's group was that can we apply some of this cavity QED toolbox to this problem, and can we enhance superconductivity without even a drive, without shining any light? So this is actually a series of work in collaboration with Victor that we have been doing. So the idea is kind of very simple to understand. You have this body of quasi-particles. We are usually coupled to a phonon bath, and then you have a gap equation that sets the gap of your superconductor. And it's usually thermalized with this phonon bath. What we are doing is that we are coupling it to a cavity at another temperature lower than the temperature of the phonon bath. So you basically cool this volume of quasi-particles, and then you effectively enhance the gap. So more mathematically, this is the gap equation. What you're doing is that you're enhancing, you're suppressing the number of quasi-particles by this auxiliary bath. And then that effectively enhances your gap. So this is a very simple way to understand it. But then once you, I skip this, once you look at different phenomena, different couplings that you get, you will see that there are some competing effects, that some of them are passed, some of these processes would enhance superconductivity, some of them would inhibit the superconductivity, and this competition will kind of changes this simple idea that I told you, that if you have an auxiliary photon bath that is at a lower temperature, it would enhance your superconductivity. It would sometimes actually worsen it, but sometimes even higher cavity temperature would enhance it. So this is the work that was led by John Curtis, and I would skip this. Another work that we've been doing is that does the squeezing enhance mediated interaction? And this is actually related to usual quantum optics, that if you put some emitters in a cavity, one can enhance the interaction between these spins. And it was not very, very well understood, because usually people thought that this can always enhance it, but it's kind of wrong. You have to enhance the specific quadrature over here. So I won't go into the details of it, but basically the idea is that you have a bunch of emitters or electrons in a cavity, you squeeze the vacuum and you enhance the mediated interaction between these emitters or between the electrons. So this is the case of an emitter. If you do it for a superconductor, indeed, you can enhance the superconductivity. So you have a superconductor, you squeeze light inside this cavity, and then you may enhance your pairing. That's it. So with this, I'll skip other parts. There is other works. We have heard a lot about this Moiré superlattice and the superlattice structure that we can make by twisting bilayers of the system. One idea that we have is that can we use light? Can we just use one layer, not doing passively, because once you rotate these, they're kind of fixed. Can we just use one layer and then use and structure light to imprint that super lattice structure on your system? And indeed, that is possible to do. And we've been exploring what kind of ideas one can have on that front. Can we use this dynamical freedom in light that we can reconfigure the system and then imprint interesting superlattice structure on an electronic system? This is very much inspired by the work on atoms using optical lattices. So now we are kind of borrowing back that idea for solid state systems. So with that, I gave it a summary, and then I just advertised some of the other works that my group has been involved with. One is looking at the connection between measurement-induced phase transition and quantum jump formalism in quantum optics. This is a very hot topic in condensed matter and quantum simulator measurement-induced phase transitions. We've been trying to understand it from a quantum optics perspective, specifically for bosons, and understand that. I briefly mentioned this work, collaboration with Meysam Varkeshli and Peter Zoller's group on this quantum simulators and measuring this topological invariance. And then recently, we've been also playing a little bit with machine learning in non-equilibrium systems and in quantum systems. That was a work led by Ali Reza, who recently graduated, and now he's in your area in Chicago. So, and as usual, advertise experimental and theoretical postdocs positions available. So if you're interested, please let me know. So thanks a lot for your attention, and I'm ready for more questions.
Thanks, Mohammed, for covering all of the many, many, many things that apparently you're working on.
Yeah, sorry, maybe that was too much, huh?
That was great.
Okay.
So
Can see
people have questions before I start asking my questions? So I have a question about topological photonics, which I should probably know the answer to. Obviously the photonic structures, which are robust against disorder and robust against bends and things like that. Is there a way to make couplers in this way? That is to make some kind of interface or coupler that's also robust, as opposed to just these what are effectively waveguides?
It depends. So so if I understand correctly, you're saying that I want to make a wave. I can make a waveguide that is robust, but now I want to make an interface that is robust, so that the coupling between one waveguide and another waveguide, whether that could be robust. Mm-hmm. So the answer is depends, because in the crystalline one, for example, in the photonic crystal, you break some of the symmetries at the interface. So they're not strictly robust, and you just have to be lucky that the symmetry, that the broken symmetry does not completely violate your underlying symmetry that you need for your topological systems. So there are two versions of it. There is this crystalline one, and then there is this effective magnetic field one. In the effective magnetic field one, I think you can do, because at the interface you don't break the symmetry. But in the crystalline one, I think it's harder to do because you're always breaking the symmetry. Why specifically you're thinking about that? Is there a specific reason?
I don't know. It just seems useful. So Paul is asking, isn't adiabatic coupling between a tapered fiber and a waveguide an example of a robust coupler?
I mean, it's robust. It's not topological. No.
Yeah.
No. So the robustness is not related to some integer that cannot be half integer.
All right. Any more questions? All right. Well, thanks again for a great seminar.
Okay.
And I'll let you get to your meetings, which are in a different link.
Oh, okay. I don't have